Hello, this is our last video that we're going to do, looking at question 5. I've skipped question 4. Once you've listened to this video, you'll be able to go back and you shouldn't really have any problem with question 4. So, reading through the question, we're told that the lifetime of some light bulbs is normally distributed. So, let's just start with that. I don't see any information about the mean and standard deviation. There we go, we can pick it up here. Find the mean and standard deviation. So, clearly, I'm not being told those, and that's what I need to find. So I've got two things I need to find from this. If we read the rest of the question, it's found that 12% fail within 2,000 hours, 5% continue to operate after 2,500 hours. I've been given two sets of information here, which is going to help me find out my two unknowns. I'm imagining I'm going to end up with some simultaneous equations to solve. I'm going to have to use that trick from question 3, where we think about our regular problem, and then we also think about the z-scores that go with it, and I'm going to have to do that twice. So I'm going to think about the problem as it is, and then I'm going to think about the z-scores. So let's just write that up here. Z is distributed by the normal distribution. We're looking at a mean of 0, standard deviation of 1. I missed out my n here. Squeeze the n up there. Okay, so with this one I can put some of the information I've been given. I don't know this. I know that 12% fail within 2,000 hours. So 12% have a lifetime of 2,000 or less. So that's 0.12. I can mark that on my standard normal distribution. I know the area's got to be the same. I don't know the z value, how many standard deviations this is away from the mean, but I do know the mean here. So I can use my inverse normal function, which we've been practicing throughout these videos, as I have the area, the mean, and the standard deviation. And I'm going to call this Z1 because I'm going to have another Z value down here. I'm not going to go through the calculator sequence because we've done that a few times now. I know that the probability that Z is less than Z1, that's a 1, is equal to 0.12. So Z1, once I plug it into my calculator, comes out as negative 1.17. I think we need a few extra digits than that, just because we're going to be giving an answer to 3 significant figures. I'm going to go a bit beyond for now. So that is 7 significant figures. That should be plenty. If you're not sure, you can always store a few more somewhere in your calculator. Okay, on to the second bit of information. We're told that 5% continue after 2,500. So from that information I can see that my mean's got to be somewhere between 2,000 and 2,500. So I've got 5% up here, which means I've got 95% down the bottom. There we go, that's 0. We've got 5% up the top, and 0.95. And this is Z2. I don't know what Z2 is, but I do know that big Z is less than Z2. The probability of that happening is 0.95. Remember, our inverse normal works from the left, so that's why I'm thinking about the bit that is unshaded rather than that's coloured in blue. Z2, going for the inverse normal on your calculator again, we get 1.644853. Let's stop there. So I've got two Z values now. I can use that formula that we have for the normal distribution. Z is equal to x minus mu over sigma. I can do it once with this information and a second time, and then I'll have two equations, two unknowns. So this is for Z1. Negative 1.174986 is equal to x 2000 minus my unknown mu over my other unknown sigma, and the same over here, 0.644853 equal to 2500 minus mu over sigma. So obviously the mu and sigma are the same for both of these situations. It's the same set of light bulbs we're talking about. This is clearly a calculator question. We did a lot of calculator work here. We can use Polysmalt to solve these simultaneous equations rather than having to deal with these fairly nasty decimals. All you're going to have to do is get it rearranged in a way that Polysmalt can accept. So we need our two variables on one side and a constant on the other. So I'm going to multiply sigma up here, and I'm going to add mu on. So I've got mu and sigma terms on the same side, and this 2000 will be left on the right side of my equation. So I'm going to rearrange this to mu minus 1.174986 sigma equal to 2000, and I'm going to do the same down here. Oops, not equals, mu plus this time, as that's positive, 644,853 sigma equals 2500. Okay, let's just do that. Let's try and tidy up a little bit. Sorry, there's not a lot of space here. So I've got equation 1 and I've got equation 2. I would enter this data into Polysmalt now. So I'd have 1, this value, and 2000. In fact, let's do that now. So we need Polysmalt. I do hope your apps don't look like this. If you do, please speak to your teacher so that we can clear some of these out. You're not allowed all of these. We want the simultaneous equation solver. We've got two equations, two unknowns. Might just choose decimals. Okay, so I've got 1, then negative 1.174986, and it went with 2000. Okay, and then my other equation is 1 and 1.644853, and that went with 2500. Okay, just be careful with the negative, that it's in the right place. So we had the negative from our first equation, the second is positive. Okay, then we press solve. We are going to get two values. It should be fairly clear that the 2208 has got to be our mean, because our mean's bigger than 2000 and smaller than 2500. The other way we know that it's 2208 is the mean is the first value we put into the matrix was the mean of 1, the coefficient of the mean. So they've come out in the same order. So I have a mean of 2208 and a standard deviation of 177. So those would be my two answers. If you were at all unsure about those answers, you had time to check them, perhaps this is probably one of the tougher questions in an exam and you want to make sure you're picking up all those marks, you could go back to this information now. You could use your normal cumulative distribution function. We have a lower limit of negative infinity, upper limit of 2000, we've got a mean and a standard deviation, and when we put that information in we should get an answer very similar to 0.12. It probably won't be exact because there's been rounding along the way, but it should, once you round the answer, it should round very close to 0.12. And of course you could check it with the second one as well. So a much tougher problem, really quite complicated. We've got standardizing our normal distribution. We've then got using that to solve some simultaneous equations, a challenging problem. Question 4 is quite similar. It's written out without the story, just with the notation, so well worth having a go at question 4.